So I'm going to take the first few minutes to finish off some of the leftover slides from last time, and then we're going to learn some new techniques. So as you know, we talked about sampling algorithms last time, right? Sampling algorithm is a alternative to the variational methods where you are not going to do a lot of the closed form analytic computation, but you draw sample from some distributions, and then you do something against the samples to let them represent a complex distribution. In a sense, it is a much more flexible and universal technique than variational inferences. The same proposal distribution can be used for sampling many different distributions. But the core idea, underlying sampling is this thing called a proposal, right? It's allowing you to bypass, the very difficult to sample original target distribution. It could be a distribution that is hard to express in an analytic form, or hard to evaluate, given any samples. But you can use a proposal, which typically is a Gaussian, to draw sample, and then use some kind of transformation or manipulation of the sample to represent the true distribution. But if you recall, we talked about a Monte Carlo technique, right? Which is to use an invariant proposal to draw sample from, and then you either weight it, you reweight it, or resample from it, and so forth. And the other idea is to use something called a MCMC, which is to employ a changing proposal distribution of the form like this, where every time you use the previous sample to define the next proposal. And we shown that it is going to converge to the target distribution, and also it is likely to have a better acceptance rate because the proposal is catching up, different modalities in a complex distribution. But still, people may not be happy enough to work with such proposal because we are going to run into maybe cases where you still see a lot of sample rejected, or sometimes the sample not very useful. So here are two notions of the usefulness. When working with the Q, two things you need to do in practice. One is to really monitor the acceptance rate. If you really run into a regime where 90% of the samples is rejected, then you need to do something. Another slightly more misleading, more kind of hard to recognize danger is something called autocorrelation. Remember, when we are doing estimation, sample-based estimations, an assumption is that all the samples are independent and identically distributed, drawn from the distribution, right? But if the samples are correlated, then their value can be compromised. So how can we actually know we are doing the right thing or the sample are good? So just to take a look about the issue behind the acceptance rate. These are potential kind of issues, right? You may basically have a mismatch of the mode, and then samples you draw from here, for example, may actually get a poor acceptance rate. But if you have a high variance, proposal like this, again, it is not ideal. So what you want to do is to really monitor whether a proposal is giving you a reasonable acceptance rate. And here are some kind of practical, guidance about what's good, right? Generally, if your proposal has a 50% rate of acceptance, you are okay. You can actually go with that. And why it is okay, you can see that here I have some special cases where a a specific, true acceptance rate, can be even computed analytically. You can see that if you use a Gaussian to sample a Gaussian, the optimal acceptance rate is roughly at here in one-dimensional case. And if the dimension is high, you actually will approach to some numbers like this. Therefore, numbers of this ballpark is understood as good enough. Autocorrelation can be computed using this equation. If you have two samples which are k steps apart, you can compute the autocorrelation function, of the two samples using this. And you can see these two curves. One is showing a low autocorrelation, meaning that when you, have k going from small to big, you have a sharp drop of the autocorrelation. That means you have a pretty good, uncorrelated sequence. And you can get roughly identical and independent distributed samples by just picking examples every, say, 5 or 10 examples. That makes them decorrelated. And here you have a high correlation, a high autocorrelation, where the R isn't dropping over K. Then you really, really cannot do much because it basically said that you need to drop the whole sequence. Right. Okay. And in fact, you can even use this equation to compute a effective sample size. Okay. If your sample get 100 samples, what it is equivalent to another number of independent samples. So this equation gives you that calculation. So you can get a rough sense about how many samples is enough. There are other techniques of modeling the condition of the sample, of the process. One is called the mixing. Remember that there is a burning rate, that you get samples not necessarily coming from the true distribution, and you want to wait for a while, right? And so when that stage is ending, well, typically when people are doing MCMC, you sample independently from multiple chains. Basically, you are running several computers together, and each draw basically from that target distribution, and you can monitor, the convergence of, the sample. And here is what we call a well-mixed chains. You can see that these 4 colors or 3 colors are producing a sample trajectory that are not too much different from each other. That means that they probably are converging to the same distribution already. You can start collecting samples from here. And in this case, you can see that depending on how you start the sampling process with random initialization, they are still quite different, in whatever statistics they compute. And that means you haven't really reached into the convergence part. Therefore, it's called poorly mixed. Then you need to time to continue burning so that they can reach to this phase. Another technique for monitoring is to really monitor some kind of statistic, computed out of the samples. One such statistic is the likelihood of data computed under the samples you get. Say you are sampling from the hidden parameters, or you are sampling from the model parameters, and then you can plug them in to compute the likelihood of data. And the sample that is converging usually gives you the best likelihood of the data because it's a good match. Otherwise, it's a mismatch. You can see, again, the curve demonstrating this kind of Hamiltonian behavior of the samples. Right. So these are typical tricks or heuristics people use to determine when your sampling procedure is working and working well. This is different from what people do in variational inference or optimization technique, where you iterative and reach a fixed point and you monitor the convergence of a gradient type of behavior. In sampling, it is less kind of smooth in terms of the convergence. You can see that there are a lot of little zigzags. That's because sample is stochastic and the gradient is deterministic, right? So therefore, they give you some different behaviors. Okay, so as a summary, these are the take-home message you want to learn from Monte Carlo methods. And again, I want to emphasize Monte Carlo methods is viewed as a complement to the optimization technique that we studied earlier, right? The keyword optimization is to compute a gradient, okay, or compute a direction that you want to, increment the current status and move to the next status. Could be coordinate descent, could be gradient descent. But sampling is about drawing examples in a stochastic fashion, and hopefully they converge to some final, equilibrium. So to now I'm going to move to the next lecture, where you can see scenarios where these two seemingly very kind of different techniques sometimes could be combined to generate even better, results. So that's actually where I want to present you the convergence point of these two techniques. Okay, so let me switch slides. And start from this one. Okay. Actually, any questions for the MC and the MCMC methods until now? If not, let's talk about a little bit about the advanced MCMC methods. I found it's very intriguing because you can see this kind of combination of some of the fundamental technique that we studied so far. In fact, just like in every science, in physics or in mathematics, unification, convergence, and eventually compositionality, across different methods is always, a nice goal, for the field itself. And from now and then, in this class, I will be showing you, different efforts and the ways to achieve this unification or to pursue such unification, so that hopefully at the end of the class, you're not walking away with 1,000 different examples or instances. You see a few fundamental principles, and then you can improvise and combine with new methods. So let's begin with, again, a statement of why we need to do such innovation. So we've learned MCMC already, which we argue that it is a better technique than MC, right? And it also has advantage over the grading methods because, it gives you simplicity, in doing the implementation and computation. But even MCMC, which has a moving, a proposal, or maybe Gibbs sampling, which has a equal to 1 acceptance rate, can still be not so good enough. Okay, so let's talk about Metropolis-Hastings, which does have a less than 1 acceptance rate. And then we talk about the, even with 1, let's see what other issues we have. So here is a kind of a illustration of what could happen. Suppose that your previous example is in here. Is in here, okay? And you use a proposal, which is a Gaussian, to draw the next example, which is like this. So this is a symmetric Gaussian example, right? So, basically the probability of going here, 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 and here, and other direction are equal, right? So you have an equal probability of getting example from all these different places. But it is in here, this is a very interesting region, in terms of the true target distribution. Why it is interesting? Well, this whole thing, whole joint distribution of the equilibrium or the target is highly asymmetric. Okay. For example, if you are going this direction, it's very easy to move sample into a high probability region of the target, right? And but if it is going this direction, then just a tiny bit of movement will basically relegate you down to a region that is very, very low probability, right? This equiprobability contour here is very dense in this direction, but it's very sparse in here, right? So in the sense that, your proposal here really, is, at the risk of slipping into, a low probability region if it go this way. But if you move in this direction, then, that risk is lower. So in a sense, what I'm saying that this particular proposal does have the risk of having a very low acceptance rate, okay, if you just don't take extra care. At least half of the samples will be going to an extremely low probability region. Right? So that's one problem with low acceptance rate. The other problem is on the, even you are in a better place. Okay, so you are in here. You are in a rather kind of a safe region. And you use maybe a small kind of, say, even if you use a small variance, okay, like this, only in here. And then you may imagine that I control it in a way that it is going to, I use a Gibbs sampling, for example. I will have a high acceptance. But small variance, which allows you to avoid the risk, to go, across the across the cliff, is causing high correlations between samples, as we see already in the previous cases. You can compute that, and here is actually is an illustration of all these computation of all these correlations. So there are issues in MCMC. One is acceptance, one is correlation. And that's the typical behavior, under a random walk, meaning that using your proposal, you basic sample randomly, with the proposal and bet on acceptance. Now, going back to here, what would be the ideal scenario that you want to generate a sample? That by methods that maybe allowing you to do better than random walk. Maybe here is obvious. From this graph, you may want to say that, even though my proposal is like this, if I'm giving a tendency of drawing samples more toward that direction, that will get me better chance of having high acceptance rate, right? And in this case, well, I want to still keep my variance high so that I get a low autocorrelation. But again, getting the variance high is making you a risk of, maybe going this way and go off the probability. I want to maintain the direction to be either here or at least in here, so that I should not, suffer from a low acceptance rate. Right. So what I'm trying to say is that other than random walk, if in your proposal you have a way to control the direction of the next sample, then you could, avoid, low acceptance rate, and also, hopefully keep, also low autocorrelation. Okay. So that's where actually the needs arise. Some gradient information which gives me the direction of where I should go or where I should find a better region for acceptance rates, can be helpful. And also maybe I should even approximate, the distribution so that I will have more flexibilities in computing, the samples and so forth. But let's focus on this first in the next few slides of presentations. Okay. So this is advanced topic, so I need to dive into some mathematics and some historical literature just to give you some flavor, some taste about how sophisticated technologists are engineering a existing algorithm. I think these ideas are quite interesting. For those of you who may have been in a physics class before, have you heard about this word Hamiltonian? Right. It is a broader term of the energy expression, in physics literature. Right. In physics, when we talk about energy, usually we talk about potential energy and kinetic energy, right? So Hamilton is a term corresponding to the summation of that. Just for example, think about an atom orbiting, the nucleus, right? And they have a potential energy by staying on the orbit. But on the other hand, if they don't move, what will happen for an atom to stay on the orbit? They will collapse to the core, right? That means that it has a tendency of, going to a low energy state. But why they are staying on the orbit is because they move. That means that there is a kinetic energy, corresponding to the speed, the velocity of the objects that can counter or cancel the other part of the energy, right? So Hamiltonian basically is Hamilton is basically corresponding to. Okay, I need to charge my pen for a little while, I guess. Or I don't use the pen. I will. If I charge, I will lose my. I didn't bring my iPhone, so I couldn't really charge it. It's fine. I will not use the pen. Yeah, it's out of battery. Mm-hmm. You can charge here. I can charge where? Can I charge yours? Yeah, for just 5 minutes. Thanks a lot. Yeah. I can use my finger to write, so this is fine. All right, so this is basically the Hamilton, and it has the kinetic part and the potential part. And there are some interesting, transformations relates to two important quantities. One is called the position. The other is called the speed, the velocity. Okay. And then you can write down the energy state of that object using this distribution. Okay. So what it has to do with our probabilistic modeling and sampling? Well, typically we are interested in a target distribution which correspond to a subset of parameters like X. How about we call X those position parameters, right? And then with the introduction of the Hamiltonian, you actually are effectively introducing some auxiliary parameters and also a auxiliary distribution which contains those terms. Okay. So why we do that? Just give you a hint. The goal is to be able to compute easily the gradient, okay, of that target distribution versus the position parameter, okay, and in a very, very simplistic fashion. Okay. Okay, so a few words about what is Hamiltonian dynamics. It begins with the following key building blocks: position vector x, momentum vector p, and the kinetic energy and the potential energy. Now I use the notation U just to be consistent with the literature. Okay, and we define H to be the summation of the kinetic and the potential energy. And that's pretty much expressed in this harmonic system where you can see there is a kind of a slope, and you have a ball rolling over there. It has the potential due to gravity and also the speed, and the kinetic due to the speed. Okay. And these are the identities existent in the Hamiltonian system. Okay. The derivative of the first order derivative of x over t equals to the partial differential of the Hamiltonian versus the p. Okay. And there is a nice symmetry here. The derivative of p over t is equal to the minus of the partial derivative of h over x. Okay. Again, just to be consistent with the notation in the literature, we're going to use p and q to denote the position and the momentum parameters instead of p and x. Okay. So we want to use this eventually to help getting the gradient of u over x to be able to compute easily from the next example. Okay. And that's actually why you have this and this over t, because now we're discretizing the entire trajectory over the t, so that your next example can be dependent on the previous example, not only by the transition kernel, but also by the gradient. Okay. And that's how basically the gradient information can be used to influence where you draw the next examples. If you use only the transition model, there's no way for you to control that direction. Okay, so that's the key idea. And just to have an example, and here is a very commonly used form of the kinetic energy, which is quadratic to the momentum, and also the potential energy, which is also quadratic to the position. And then you can see this equation can come down in a very trivial way. You can see these are very interesting dependencies, okay, between the p and the q vectors. And you can actually use this to even derive the closed form of the position and also the momentum over time. But of course, in a real kind of a proposal distribution, your u of q is never that simple. Okay, it could be a very complex distribution over the q. But the k, which is auxiliary, for your computation of the Hamiltonian, usually are always taking the form of a p squared over 2. Okay, so remember again, this is here. U and the k, u is the potential function, which is our original target proposal. Okay. That can have arbitrarily complex form that you want to sample from. But the k is an auxiliary, which you made very simple to be taking this quadratic form. Okay. So now how to compute the next p, or next q, which is our position parameter of interest from the previous one. Well, with the help of the p, which is the momentum, which is the auxiliary random variable, you get a very, very easy update. Okay, so p of t plus epsilon, or q of t plus epsilon, actually comes from the previous one times a gradient. Okay, and as we derived before, the gradient actually can be computed from the potential, the momentum from the previous time point. Okay, and likewise, just to be symmetric, the potential also can be computed from the previous potential plus a term dependent on the gradient of the potential functions over the position. Okay. Got it? So this is called the Euler's equation. So with this, you can already, basically get a proposal, based on this. This is basically your next sample of the X, right? And you can probably go through acceptance test and so forth, and go with a sequence. People actually played with this Euler's equation. Do I have the pen already? Thanks. Okay, so let's look at this. Right, so the key idea is that now I get basically this one over this one and this one over this one, but then there is a term that is cross. Okay, to here. And this one, of course, has to be computed every time. So in a sense, I'm using a auxiliary random variable to make my computation of the next step, very straightforward. In principle, you can basically generate a sequence of Q, T, T plus 1, and all the time to this, using this Euler's equation, which is always in the direction of your gradient. Okay? But it turns out that if you don't qualify these samples, people find the sequence to be divergent. Okay. For example, we computed, we have an analytic expression in the past of this system. And if you don't take the closed form and using the Euler equation to simulate, people find that you actually get a sequence of divergence rather than the true kind of sequence, which is a circle. So why that's the case? Basically, it means that your gradient is a little bit overshot, okay, and then you keep adding to that, and you cannot really correct that. And this is because you can analyze this sequence a little bit, and it turns out that you can establish this expression of the next step versus the previous one, and it's a kind of a divergent series due to this updated equation. And how to test that? It's very easy. You just power particular transformation matrix n times and see how big it is. It's going to explode to infinity. Okay, and it's easy to see it because it is a full matrix. Okay, and you can compute the trace of this, the determinant of this, and you will find that it is bigger than 1. Therefore, it is always diverging. Okay. So that method isn't working in practice. Then comes to the next method called the Leapfrog Method, which is to make use of a half step, to update the P, and then the full step to update the Q. The Q always take a full step. The P always take a half step, and then the full step. Okay. And these equations are pretty straightforward. It is still using the Hamiltonian system where, the P dot equals to, to Q, and Q dot equals to P, and so forth. But you can also verify the algebraic nature of this new transformation. Turns out that, this new update actually is updated from this part, and the transformation matrix has this very interesting property called a shear transformation. Okay, shear transformation has a half matrix that is having 0 elements. Okay, and the other part is non-zero. And you can prove that this one has a determinant of 1. Therefore, it is preserving the volume, okay, of the system. Okay. Again, the details can be available from the little paper that I posted by Ralph Neal. I put on the website. But just to recap, as a comparison, this leapfrog method is going to give you a convergent sequence, and the Euler's method is non-convergent. Okay. Now we can see how to use such a technique to construct a MCMC from the Hamiltonian dynamics. Okay, we define now a auxiliary distribution, which has the potential part, energy part, and the kinetic energy part. Okay, and this potential energy comes from our original target distribution. Imagine that we have a Bayesian setting where Q are the parameters we want to sample from, such as the topic, frequencies, and so forth. And the pi denotes the prior, and this one is the likelihood. Therefore, we are sampling from the posterior of the Q. Okay, this is the posterior. So supposedly a very hard to sample distribution. And then the kinetic energy takes a very trivial quadratic form. Okay. So the key idea is to use the Hamiltonian dynamics now to start proposing the next step. Right? You basically start from a Q0, and then you draw the P from a normal distribution, a very, very standard distribution. And then you use the L steps to leapfrog to the next Q1, and maybe Q2, and so forth. And then you reject or accept based on the change of the Hamiltonian. Okay. Remember, this Q and the Q1 and the Q2 are basically computed using this equation. Okay. They are not a random walk from the proposal. Okay. Originally, when we use a Q of say little q to draw the samples, it's a random sample from the proposal, right? And right now we are drawing the next Q using this equation, which has the gradient information, okay, from the U over the Q. Okay. So here is basically the formula. Sometimes people don't do just one leapfrog, but L steps of leapfrog. Okay, and then at the end of the day, you are going to do a full step update, and then you can still go with the acceptance rate test. The test is a little bit tricky in here, but it's analytical and explicit. Okay. And you can prove that this formula still gives you the detailed balance. It is algorithmic, and but it has a better property in terms of say the autocorrelation and also the acceptance rate and so forth. So for example, in here you can see this random walk metropolitan versus a Hamiltonian. You can see that the samples you draw are much more concentrated on the high probability part of the distribution rather than going other directions. And you can also see the 2D examples where, again, here you can see what? Some kind of autocorrelation structure, right, across samples. But in here, you don't have such autocorrelation anymore. And this is a 100-dimensional Gaussian distribution, which is even harder to draw. And usually, in higher dimensional space, you are very unlikely to move out of the neighborhood of the previous sample if you do MCMC. Remember, MCMC is the defined proposal from the previous example. In a very high dimensional space, it's very hard to escape from the kind of the modality defined by the previous examples. Therefore, you see this extremely high autocorrelation. But now, because we have a gradient correction, okay, over the next example, you are more easy to escape from that, and therefore the samples generated are much more uncorrelated. Okay, so here are some numbers. You can see that the acceptance rate now becomes a lot higher. Do I have the? They didn't put the autocorrelation, but I can see it from the graph. Okay, so that's Hamiltonian versus MCMC versus standard MCMC, random walk MCMC. Then along this idea, which really promotes the use of gradient, over the sampling procedure, you can see the idea. The gradient belongs to OPT, right? And then the sampling idea belongs to MCMC. That's why you can see this marriage of the two seemingly very different approach now to together produce high quality samples. So along this idea, there has been a lot of kind of a little innovations or heuristics to make it simpler or more effective in certain circumstances. For example, here there is another algorithm called the Langevin MCMC. That's basically the case where you do only one step of leapfrog. Remember, in our previous algorithm, which is a very generic algorithm, you can do L steps of leapfrog before you test that example. Okay, it's to really allow you to move arbitrarily far along the gradient, and then see whether it is accepted or not. But if you only want to do one leapfrog, then the algorithm can be aggregated into a more compact one. You just basically, bring in, for example, this term into here, and then bring in this term into here, and replace, the intermediate steps. You can actually get a pretty compact expression of the new Q and P as a function of the older P and the older Q, one step away, not a half step away. Okay, so you can derive this hopefully just from here by yourself, and then that also requires a acceptance rate test, which is defined by this particular proposal. Okay. So why this is kind of sometimes favored? Because it gives you a very clean way of exposing, how to compute, the gradient of the likelihood function versus the position or versus the parameters, in a single computing step, where all the issues you are going to run into, for the calculation of the gradient can be solved at once. For example, one of the issues is about the size of the data. If you have a large data set, then computing the whole gradient in here, of course, can be quite complicated, right? Quite expensive, because it requires a summation over all data sets. Then the stochastic gradient Langevin is to allowing you to really have some control over the size of the summation. Okay, you can basically select a subset of the samples to compute this gradient, and then hopefully go back to here. So this is not quite the same as the full gradient. Yeah, but again, remember that we can treat this as just a compounded proposal for the next example. They will be qualified using, eventually, a acceptance, test. Therefore, wrong examples will still be rejected, but the high probability examples will be taken. So in this way, you compute the gradient in a much easier fashion. Okay. So you can see, all the technique we developed in the optimization literature, stochastic gradient, conjugate gradient, can all be applied in here to, augment, the proposal distribution for the next example. Okay. So in some sense, what you see is now, maybe a practice or maybe a exercise to come up with more expressive and effective proposals. So let's look at originally, we go with a proposal of X, which is easier to sample with regard to the target distribution X, right? But we are going to use that proposal forever and use rejection or importance weighting and so forth to qualify the examples. And then next, we start to use a proposal that is moving over time so that it will be, here it's converging to X, right? And here includes, Metropolis Hastings and Gibbs and so forth. Here you have importance and weighted sampling and so forth, right? And then, what we taught today is a upgrade of the second technique so that it is going to be X, come from, a oracle which contains the proposal, okay, and also some gradient information. Okay. It's about you draw it from here, and then you are going to plug them into, the gradient, increment, and then determine the next examples. So in a sense, it is another proposal, but it's not, expressed in a analytic form anymore. It is in a oracle that has two steps: draw random example from here, and then, leads to a gradient increment, and then that gives you the next X. Okay. And also the proposal are not directly coming from X. It's actually a proposal of the P, of the momentum, because that makes the gradient calculation even easier. So this is basically the whole kind of sequence of technique that people developed, over the history of MCMC literature, so that you can, really, enjoy basically, both the efficiency and also the simplicity of many of the computations needed, for computing or do inference under the original full distributions. Okay, so I'm going to be pause for a moment here to take any questions. So here are some take-home messages. Any other questions so far? So there's a caveat. Hamiltonian MC is not usable for discrete variables. Do you know why? Yeah.
Because you can't take the derivative?
Yeah, you cannot take gradient on discrete variables. Yeah. Any other questions? No? Okay. Then let's look into some of the supplementals and see whether we have even more ideas to play with. Again, this whole area of approximate inference, is still very active. Okay, there are a lot of techniques that we can cover, but I'm going to just pick on some bigger ideas. We can still do better on the proposal from another dimension. Okay, so that's basically the topics in the following few pages. So far, as we just wrote down, there are a few ideas for proposal. One is just trivial proposals like a Gaussian, and the other is slightly less trivial, a moving Gaussian that is defined, on your previous example and so forth. And then we have yet another, fancier one, which is draw proposal from Gaussian and then use it to compute a gradient and then come up with the next examples. It looks like that Gaussian entity or whatever trivial distribution you can draw from is the key, for building a proposal. In a sense, in building a proposal, we don't look too much into the P, the original target distribution, except in two places. Again, I'm using this as a review as well to go back to what we did so far. So in the previous places, three algorithms, MC, MCMC, and the Hamiltonian MCMC, where are the original P distribution touched upon? I can remember two spots, actually three spots. So in MC, when do we look at the P?
Calculating acceptance probability?
Yeah, when we are calculating the R, or maybe the weight, right, we look at the P. But we don't look at the P when we deal with the Q. Okay. And in MCMC, when do we look at the P? It is also in computing the acceptance rate. It is when we compute the A, we actually look into the P, right? Now, in HMC, when do we look at the P? The original distribution. There are some difficulties in notational swapping. Remember, there was a step where we compute the U over X, something like that, or U over Q. The U actually is our P, right? It's our original target. So that's basically, it is when we are looking at the gradient over X that we look at that. So in a sense, we are looking at that for the proposal already. The proposal itself is influenced by P, but in the way that is a gradient. There is another technique that arguably is simpler, where your Q could directly take advantage of some knowledge about P. Okay. So remember our variational inference recap. The variational inference is about really introducing a surrogate distribution over the hidden variables, which satisfy this lower bound. And instead of computing the P, we're going to compute the Q. Right? So that's basically in the variational inference literature. And we argue that the Q is close enough to the P so that you can use it for inference. Okay, so we'll choose this. Okay. So that's variational inference. Your whole goal is to compute this to approximate that. The other caveat is that what about we also basically move the target in here. We also replace this with another set of parameters. Okay. And make this P also a little bit easier. So it's like I'm having a complex one, P, and I'm using the Q to move up and approximate it. But now I'm also start to approximate P in here. I'm going both way. Okay, and therefore maybe at the end of the day I'm going to have this one, which is reasonably close to the true, but on the other hand making the calculation of the Q easier than before. It's becoming a bit hairy, but that's actually what happened. In the next few lectures, we're going to discuss some deep neural network algorithms such as variational autoencoders and wake-sleep algorithms. They actually start to fall into this category of business where at the end of the day, people forget about the original target to optimize. People are focusing on an oracle, which basically is iterating between some P and some Q and converge. Whether that P is the original P, well, maybe, but it's not quite the same. Okay, so that's kind of the bigger idea. But the whole goal is really to draw this, basically these two things close to each other to have something that is workable. That's the whole point. Okay. So that basically, is used in, MCMC in the following way. You can now come up with a proposal that is said to be that approximating, distribution. Okay, which is, easier than the previous P. Okay, I make that as a proposal. And if you are able to solve a variational inference problem where the P is close enough to the original P, then you may have a good acceptance rate. And then they eventually will hopefully get you faster to converge to P. So let's see, what's the rationale here? What's the whole picture? I think this is already getting lost. We want to sample from X, okay, and we start from in the variational inferences we do this with a Q of X, okay, and typically in VE we directly minimize the KL between P and the Q and P. That's in VE, okay. And in variational in MCMC, you basically are getting this up and getting this down to a point which is a P of estimate, okay, through some KL measure. And then you use this as a proposal and do sample again and hopefully still move to PX. Are you still with me? Okay. So it's becoming a kind of a heuristic and a greedy push. In VE, we know that the variational inference, is not going to get you to the true distribution. We knew that because we're already choosing Q to be a approximating family of the original one, which may not include the original distribution. Right? Remember the marginal polytope one? It's a sub-polytope, right? In the mean field cases, and we're going to stop there. Okay, but in here, you get to this point, you are not going to stop. You are going to use that as a proposal to push further to P using a sampling scheme. So that's another way of combining the OPT, versus MCMC. This part is OPT, and this part becomes MC. Okay. Kind of awkward, but that's what can be done at least in principle. Because proposal can be anything, As long as you are able to draw sample from here, we just let the proposal to be the solution of our VE, and then go on with the sampling step. Okay. And also, it can be iterative, because once you get the sampling part, you actually are filling in the hidden parameters, and almost like rebridging the E step using sampling, and then you can recalculate the approximation and gets it even closer. So this becomes an iteration loop. Okay. So that basically gets you a neural algorithm which is arguably giving you better results in terms of the likelihood estimation. Okay, so that's the new idea, adaptive proposal. Using the variational inferences, it increases the mixing rate, and with all these nice properties that we expect to come from. Okay, so basically idea 2 on MCMC plus OPT. Okay. Questions? Yes.
Does it do better than Hamiltonian Autocorrelation?
Good question. I don't think it is really meant to be compared. They are just two different methods, each of which work in their specific territories. When they are both used, actually I don't know a literature where you have a square comparison. Because in here, here is how you can see it. In fact, these two OPT methods can also be combined. The Hamiltonian methods really help you to draw samples from a complex distribution where you can take a gradient towards that hidden variable, for example, the parameters, right? And it's kind of narrow, for example, continuous distribution only, and not discrete. But this approach is very general. It's like a bigger graphic model of arbitrary form, and then you just need to sample any hidden variables of interest in those graphic models. And therefore, the proposal is not just analytically difficult, but it's very, very compounded, very, very complex, in terms of the structure, not in terms of the algebra. Variational inferences, the variational approximation as a proposal allows you to work on a approximation that is manageable, in its, basically you can imagine that my Q of EST could be just a simpler one, which has this discrete, the factored form, for example. And therefore, that allows you to sample each of them independently, for example. So this is a structured design. Okay. And then how to sample each from them? You can use the Hamiltonian MCMC to, again, do it. Right. So I think they are designed for different levels of sampling complexity and task. Okay. The Hamiltonian one is more about overcoming the analytical algebraic difficulties of getting good samples. Okay. And this one is more about structure. Yeah. Good question. Other questions? So this lecture is a little bit less structured because I'm just threw at you, a bag of different tricks. But what's the gist of that? You can see nowadays people are talking about compositionality in machine learning, meaning that you want to bring in different techniques together in a composable way to solve larger scale problems. And also larger scale problems is always more than just a single algorithm or a very simple model. So here you can see the ideas, right? When you are working with a large model, say a deep generative model of many, many layers, how do you sample? This is a very generic question. There are maybe 1,000 parameters or variables for you to sample. And with what we learned so far, you can see, so this large model could be just f of a gigantic x and theta. And you need to sample from that. It turns out that you can divide them into, a product of maybe f1, f2, and all these subfunctions. And each of it basically contains a subset of random variables you have to draw samples from, or you have to estimate. Some of them can be taken care of by a Q, just a direct variational approximation. Some of them can be approximated by a sample, but then you have maybe 3 different ways of sampling it. One is to overcome the algebraic complexity using Hamiltonian. And one may need you to break it down further into smaller approximations and use MCMC or variational MCMC to sample from. So basically, different methods can be combined to work on a larger model of all different facets and needs. Right. So that's where I think the research become complex and heuristic. People actually did try this, in many ways. Okay, so I still have a few minutes. Let's together look at yet another sampling problem and see, where it can be used. Do we still remember this? This is about weighted resampling. It means that you may get samples which are misrepresenting the true distribution, in the sense that you accumulated a lot of samples in the low probability region of the original distribution just because your proposal is too bad. Okay? And then in the high probability region, because of a mismatch, you don't get too many samples. But then you can start computing the weights of all these samples, which gives you this equation. And then you can now do a pass of this sample to kind of re-instantiate it, right? And that basically gives you, hopefully, the more correct kind of expression of the true distribution using samples, just by redrawing some of the high-weight samples and discarding some of the low-weight samples, even though they are very populated in the previous round of examples. So that's the idea about weighted resampling. This idea has been used, in a task known as the sequential MCMC, and leads to an algorithm known as the particle filtering. Okay, so the sequential MCMC is, is basically to sample. It's essentially this problem. Actually, let me see. I didn't prepare this part, but let's see. Imagine that we have a hidden Markov model with very complex transition functions, P of x. Do we use x or y? Yeah. P of x, t plus 1 given x. Say this one is kind of complex. And then we have also the y's, which are the emissions. Okay? And I want to maintain a distribution of P of xt given all the examples of y to t so far. Okay, that's my task. And we know previously the forward algorithm for the HMM, which is very, very handy and discrete. But what if it is a continuous distribution, or it's a distribution where this particular expression is very hard, for you to compute? So here we have a sampling-based approach. So the starting point is that you have this already, which is the current distribution of the last hidden states given the sequence so far. Okay, and this distribution, can be sampled from, right? And we sampled the following way. We rewrite this distribution, okay, and using this breakdown, it's just to basically separate the contribution from the sequence up to time t minus 1, and also, the emission probability of, basically this is xt, this is yt, and then there is a whole bunch of other sequences in here. Right? So we want to basically separate this part and that part from that rewriting of the conditional distribution. And by looking at this equation, you can already see that this is equivalent to drawing samples from this part of the distribution and then weight every sample from that equation. Can you see that? Right? It's a typical way of expressing basically a distribution using the samples. So we now express this part as a set of samples. Now our goal is to introduce one more piece of information, which is yt plus 1. And also we want to now compute the p of x t plus 1 given this new example of t plus 1 plus the older case. Right. So this is set up. You start from a previous distribution, which now is represented by the samples, and then receiving one more evidence, and then you update into the next one. Okay. And here is the equation using the sequential MCA technique or using the weighted resampling technique, because you can establish a connection of this time update with respect to the previous predictive distribution and also the transition model. Okay. So basically, you are going to now build a time estimate of the new state only based on the previous distribution based on using the sample up to last time point over the transition model without seeing a new evidence. And this equation is expressible by what? By the samples, right? So remember this one is this one, right? We use a sample to express the previous hidden variable distribution. And then now this integration over this can be now replaced by a plug-in of all the samples over this transition model. Okay, so this is called a time update. So what you do is that, from the previous distribution, now you basically can express this time update using, this weighted sum of the transition model based on the reweighted samples. And then you bring in the new evidence, and that's the equation of the newer predictive distribution based on the previous predictive distribution with time update and also new evidence. Okay. And in here, this part is already known. And let's see. Okay. So this part and this part, we actually knew how to draw sample from already, from the time update, right? And this part and this part is basically, a way, it's basically a weighting of the samples from this distribution. You can see, okay, from the normalized weight plus the normalized weight. So that basically can be again expressed by samples, where I draw this sample from this distribution, which is already expressed in here, and then update the weights using this equation, using this emission model. So the same picture here, you started from that distribution in here, and then you are going to draw samples from this distribution, which is the time update in here. Okay. And then you are going to compute the weights of the newly drawn example, which gives you that. And then this weight and these examples will give you the expression of the next predictive distributions. You can see from here to here, we have the time increment on both the hidden variable and also the evidence. And what you are propagating are basically a set of samples which gets sampled, weighted, and resampled. Okay, so this is known as the particle filtering. People view this as particles, and just you filter through these particular phases and keep propagating forward. So this method is very, very popular in sequential inferences, because in many of the sequential models, your distribution over a transition model over X can be very complex, like this. This is a transition where the hidden variables are like this, are 3 layers, okay, with the continuous and the discrete. This is known as a switching state space model. We haven't talked about common filter, but this is even a more elaborate inference of that. The point is that sampling this distribution is very, very difficult. Doing inference on these hidden variables are very difficult if you use any analytical methods, such as HMM, z-stat inference, or even approximate inference with a variational technique. But you can easily maintain a sample of all this over time using the sequential Monte Carlo, because you can see that all you need to do is to be able to start from some set of examples and then compute a weight using the emission. In this case, the weight is basically the emission of this guy given the 3 guy. That's actually really easy. Okay, you can compute the weights. And then you can just filter the particles using these weights into the next phase and maintain basically a moving kind of collection of examples. So this technique has been used for many of the kind of online tracking, fault detection, and so forth under either arbitrary kind of complex dynamic models and emission models. I give people the freedom of introducing complex models for time series modeling. Okay, so with that, I think I covered a couple of techniques in sampling-based approaches. And there are a lot of variations of this based on the task you have to work with. I think I'm going to close here. And starting from next time, we will be presenting a battery of deep neural network models, starting from its origin, coming out of the graphic model literature. And then we see how people evolve this technique into a lot more application-oriented innovations and inference technique. All right, thanks.